simple. We all know that pollution is everywhere. So sensing is becoming very important from that perspective. Now, what is sensing? Sensing is detection and or estimation of pollutants in analytes or essential or fatal metal ions in bloodstream or in any thing that we intake in our body. Now, why do I put this essential slash fatal both together? You see, like copper ion is essential element or essential ion in our body. If there is no copper ion, then many of the enzymes they cannot work. But at the same time, if the concentration of copper ion goes beyond the limit, then it becomes fatal, and you get the skin problems and ending up with cancer. So, sensing of the things are very important. Like in pollutants like cyanide, arsenic, and this essential or fatal metal ions like potassium, sodium, copper, and many others. Now, what are the methods? Existing methods. There are many in fact. Liquid chromatography, potentiometry, capillary electrophoresis, etc., etc., etc. But fluorosensing is the most sensitive one because of its super sensitive character. So, very little amount of substance can easily be detected and estimated, of course. Now, what are the ways? There are basically two ways that we can use for this fluorosensing. One is enhancement-based fluorosensing. That means you have the sensor, which is nothing but a fluorescent molecule. Sensor is there, and you add the analyte for which you want to sense. So, upon addition of the analyte, there may be fluorescence enhancement. That means the first emission was very weak, but as you go on increasing the concentration of your analyte, fluorescence goes up. This is called enhancement-based fluoroscensing. The other is the quenching-based fluoroscensing. Here, as you go on increasing the concentration of the analyte, the fluorescence intensity decreases. In fact, in our case, we use the second one. Now, for fluoroscensing, what are the major criteria? There are basically two. One is selectivity. You see, the sensor must be selective to one particular atom or ion or species, or maybe at the best a group of ions or atoms or groups, whatever it is. So selectivity is essential criterion. It must be there with the sensing parameter or sensing criteria. Because if you add something, a sensor, and then whatever you add, there is fluorescence enhancement, or maybe fluorescence quenching, and it doesn't work for us. It cannot be a sensor. So what is the other one? Other one is sensitivity. That means a little amount of analyte should be able to change the fluorescence behavior of the sensor hue to a good extent, so that we can sense it. Now, what about selectivity? It's a matter of luck. I don't know if I start with a fluorophore, whether that will sense to someone or some entity. I don't know. So it's a matter of luck. You go on trying. If it works, that's fine. If it doesn't, you have to throw it out. But what about sensitivity? Sensitivity, yes, there are ways. First of all, maybe we have some molecule, some sensor, which senses it, but not to a good extent. So, what do? We modify the molecule, this base molecule. So, we modify it maybe by adding some group, by modifying some group, and so that through synthesis, we get a better one, better sensor, and we can use that one as efficient sensor. But to me, it's frightening. The synthesis is very difficult to me. So, I take a rather clever and simple way, that is modification of the environment. So, that is the thing that was published in JAX, and the objective was to enhance the sensing efficiency of a sensor enormously, bypassing the synthetic loop. So we did not put any effort to synthesize or modify the molecule. Now, what is the approach? You see, this now I am addressing mostly to the youngsters. You see, the approach is very simple. While doing research or doing with science, one thing you need to do is you have to correlate or translate science contents from book to the society and vice versa. So from society also you can learn something which you can translate into science, and that is exactly what I did with this next paper. What was the basic idea? Whenever you are in a new city like Kolkata, you are to stay there for maybe a year. So you need some residence or apartment to stay there. But you do not know which one is vacant. So it's very difficult task. The similar way, there are plenty of people who have their vacant houses or maybe apartments, but they also do not know who are the prominent or potential tenants. So although the giver and taker both are there, but there is no handshake. So what do we do? The owner of the flat, they just communicate to someone, some person called broker, or in Bengal is dalal. So broker, they give the information to the broker, and the needy person, like the newcomer, he also approaches him, and then that broker makes the handshake possible. Okay, that's the beautiful concept of the society, and I just translated it into science. So what did we do? Basically, we modified the environment by introducing something to serve the role of a broker, and that something was myself. Now, here in particular, we try to sense copper 2+. So it's a positive ion. So to materialize our idea, we chose selectively anionic micelle. So the units, micellar units are there, and the surface charge is negative. Okay. So what is the benefit? Now before knowing this quenching-based sensing process, we have to know what is the basis. The basis is you excite the fluorophore, which is sensor, and it has some fluorescence light, particularly for our system, around 1 nanosecond. So within 1 nanosecond, the analyte has to come to it and interact so that their energy goes there and the fluorescence goes off, or at least reduced. Okay, that is the basic principle. Now, concentration of the analyte is in micromolar region, and of course, concentration of the sensor is also in the micromolar region. Micromole means one probe surrounded by 10 lakhs of solvent molecules, roughly. So it's mostly solvent molecules. So basically, when we use both in the micromolar range of concentration, they are far apart. So within 1 nanosecond lifetime in the steady state, these quenchers, which are really analyzed, but effectively quencher here, they cannot come here. So this molecule, we come to it, the molecule, even if we add copper in the micromolar range, of course, of concentration, there is hardly any quencher. So what did you do? It's a situation like they are there, but they cannot meet. So what did we do? We used anionic micelle. What does it do? And to help the process, when the micelles are there in the solution, we added them externally like broker. So the fluorophore, that is sensor, that sticks to the surface or boundary of the micelle. Okay. So now they are more localized. At the same time, they stay on the surface of the micelle. And now micelle is negative. So it has a natural tendency to attract all the positive ions. So now the copper ions are very close because micelle is negative and copper ion is positive. So they are very in proximity. So what happens when I excite the fluorophore now? Even because of the attraction or interaction with the micelle, basically the sensor is sticking to the micelle. So the fluorescence lifetime also goes up from 1 nanosecond to 2 nanosecond. So it's basically 100% increase in lifetime. And then added to it is the proximity of copper now. So within this 2 nanosecond lifetime, there is efficient quenching of the fluorophore by the copper pointer. These are the two. This was first one, and then it is so powerful that we used it in later time, maybe 2 years gap is there, 2006 and 2008. Yes. So it got published in Journal of College and Literature Science as a priority communication, which is very rare. Anyway, so I just skip this thing. So basically, whenever we use the micelle, then we see the quenching is much more efficient. Okay. Now, for quenching based experiments, most people know that we often use Stern-Verman equation, which is fluorescence in absence of quencher by fluorescence in the presence of different concentration of quencher, and it follows the equation, Stern-Verman equation, 1 plus Ksb Stern-Verman constant into quencher concentration. Here it is copper concentration. Now this Ksb, the more efficient the quenching is, the more steeper it is. So basically value of Ksb is an indicator for the sensing efficiency of the sensor towards the ion. Here it is copper ion. And sensor is some molecule AODIT, we call it. So now what do? We start with simple aqueous solution. That means in absence of SDS, sodium dodecyl sulfate, it's anionic mice. And sensing is very poor, like here. And then we go on adding different concentrations of SDS and perform the entire study, right? So this single point is a complete experiment. So we go on varying this SDS concentration and got a curve like this to put plotting Stern-Verman constant against SDS. So basically the efficiency of quenching, which is reflected by the value of Ksb, goes up, you see, it goes to very high value. The increase is more than 2000 fold. It's enormous increase. Okay. So our objective is basically, as is evident from this one, we can tune the efficiency. Of course, tuning is not our purpose. Our purpose is to obviously maximize it. So we can maximize at a particular concentration, which is nothing but the CMC, critical micellar concentration. So with this experiment, we can tune the sensing efficiency in a sense, but most importantly, we can easily optimize it, maximize it, and Ksb generates by more than 2000 fold. Okay, and to give the I don't like the words limit of detection, etc., but the practical thing is addition of 20 micromolar copper quenches the fluorescence to 50%. So 50% is enough. Half the quenching goes to the half. The fluorescence intensity goes to the half. In fact, with a stable instrument or fluorometer, 5% change in the emission can easily be detected. So if that be the limit, then we can easily measure 2 micromolar copper, which is well below the limit. Okay, that's good. The first one is done. Then how powerful it is. So in the first one, we used a neutral molecular system, AODIT, organic molecule, but it enhanced the sensing efficiency 2000 fold. Now we ask the question to ourselves: if we take a cationic fluorophore, is it possible to sense copper ion again in the same way? The common answer is no, that cannot be. It should be non-sensor because they are in solution. So when you excite this phenosafralin molecule, the basic thing, this chloride goes as or stays as counter ion. So basically the fluorescent unit is positive and copper ion is also positive. So when they come, there will be obvious statical repulsion, static there is electrostatic repulsion, so they cannot come closer, so there will be no interaction in that sense. But our method was so powerful that even with this technique, that means introduction of suitable mine cells, now I am adding the word suitable mine cells, you can very efficiently detect cation using a cationic fluorophore reported for the first time in science. At least to my knowledge, this is the first report. Okay. Now if see, now I have just used suitable. So what did we do here? The same experiment we repeated for different surfactant molecules. Okay. So we have now changed the mindset. The first one is S8. S means carbon chain is there, of course, and 8 carbons are there. Okay. So this is sodium octyl sulfate, something like that. So this is carbon 8, this is carbon 10, this is carbon 12, and this is carbon 14. So gradually we have increased the carbon chain. Okay. So nature of the gross nature of the micellar units remain the same, but there are of course differences. Now you see, this is the concentration of the micelle or surfactants, and ordinate gives the Ksb, which is basically representing the sensing efficiency. Now you see, I would request you to kindly note carefully this value. So this maximum goes to 250, this goes to 800, this goes to 3200, and this goes nearly to 15,000. That means with a long chain sodium, this is tetradecyl sulfate. If we use, we can very efficiently sense copper ion. So thus we were able to detect copper ion and sense copper ion by using a cationic fluorophore. That is very interesting. Now going to another thing. My whole intention, of course, targeting towards the youngsters, is that if you have open eyes, you can develop some strategies which are really important. Now you see, many of you, maybe most of you, work in the field of nanoparticles. I also worked for 2-3 years, and then I got bored. Because mostly what is done, A is mixed with B in some condition, and some precipitate goes off, and we then purify, and we measure, put the sample in on 10, same, 8, and we get some structure, dimension, okay? This nanometer, and then we do some research, that is etc. But I asked myself, is it not possible that I will dictate what is the size of this thing? Because what is happening in all other researches, we have to use same, each one of them, each one of these instruments cost more than a crore. That means most of the weak or poor universities, they don't have these instruments. So is it really a bar for the poor people from doing some interesting research? No. So we developed a simple strategy, very simple strategy, where from you can measure, you can prepare at least gold nanoparticle that we did the research with. You can prepare the gold nanoparticle of your desired dimension, and you need only a spectrophotometer to confirm it. The spectrophotometer is very cheap instrument, and most of the universities have in plenty of them. So now let's go. So major problem was size of synthesized nanoparticles is known from 10, mostly 10, and then same 8, and they are very costly. Cited reduction method, which is called also French method, it was discovered or developed by French. This is a standard method. So there is nothing that we develop. We only use the strategy. We only develop this new strategy. What is that? So cited reduction method of preparing gold nanoparticle was used. What does it do? You take chloroauric acid and just reduce it by mild or mild reducing agent like sodium citrate, trisodium citrate, something like that. That's the standard protocol. So we have developed a strategy to synthesize gold nanoparticles of desired dimension. That is important. Of course, we have done our experiment within this range, so I cannot claim what will happen if the dimension goes below or above. So within this thing, we are confident. So what did we do? We varied the composition. Okay, as I said, chloroauric acid and citrate, trisodium citrate. We varied this relative concentration. Okay, and that's the only thing. Now you see, as we varied the thing, the sizes were different. You can see from this figure, and this one was one side, and obviously this is bigger, this is even bigger, this is the biggest one. So we have only 4 dimensions because we had to get it to 10 again for standardization. Okay? So we did not have 10 at the time, so we had to get this thing done from IIT. Anyway, so we were limited to measure the dimensions for 4 samples. But we have spectrophotometer in our own lab. So with these 4, what did we do? We also got the or measured the lambda mass for the solution. It's not solution, of course, it is colloid. So we got it. And then, what did we see? Okay. So here. So we plotted this diameter that we got from 10 measurement and lambda mass. And we got fantastic straight line, very good straight line, linear. Okay. Now we did another experiment. We varied the fractional concentration, as I said, and we just simply took the lambda mass of the sample. And since here the instrument is with us, so we could do it for a large number of experiments. And you see, here also we got a very good straight line. So then, what we intended to do is, we plotted diameter against fractional concentration of the cell. So we get again a very good straight line, from which you can get simply an equation of straight line. That means this diameter now is correlated through a linear equation with the fractional concentration of the reducing agent or reductant, right? So now the simple people, the poor people in the universities particularly, they can use this strategy. So if I want to prepare gold nanoparticle of 40 nanometer diameter, I should go there and I should use this fractional concentration till for this 0.6, something like that. That means relative concentration. It should be like that. So simple, okay? And believe me, I have got a large number of communication from different parts of the globe, particularly from the weaker section, weaker in the sense of money, poorer sections, that it helped them it helped them a lot to do some research on nanoparticle science. But of course, it is very critical to get the absolutely exact dimension. Of course, it is not important in that sense in majority of the cases. Then you should go for 10, 10, AFM, etc. I am not ruling out their values. They are definitely valuable, but we don't have, many of us we don't have. Okay? So now going to the other. Improve delivery of drugs to target. So how can we improve the delivery of drugs to target area? And more interestingly, excretion of excess drugs from the body. Now, if we see, there is a sentence like medicine is the science and art of healing. Of course, we have to survive, we have to use medicine. So, for different ailments, we use different medicines, and effectively, our body can be symbolized like a host of medicine. Okay? So, the main concern of us now is how to get rid of this thing, this side effect. So, that's very important question we should ask nowadays to ask. The ways to get rid of the drug-induced side effects are, we find, two. One is, if we can deliver the drugs efficiently to the target area, target region, then the dose of drug will be less, so side effect will be less. So, one aspect important is the delivery of drugs efficiently to the target. And what is the other? The other one is very simple idea that came to my mind, that you see, that whenever our garments get dirty, what do? We wash it. We use some detergent and we wash it. That's it. So can we not wash our body inside, from inside? So if wash means clean the excess medicines from our body, is it not possible? So that was the idea. So to expel the adsorbed drugs from the body, okay, like we don't wash our clothes every day, no? So it is the same way. So it is again translation of the societal or family-wise also, societal picture to science. That is the only thing that we do, and that is very efficient. So two major approaches of drug delivery is for the young people. One is endogenous, the other one is exogenous. The basic idea to transport or carry drug is to bind the drug into some micelle or liposome or cyclodextrin, something, so capping agent will be there, so that when it goes there, the drug is not taken up throughout the body, because that will be very detrimental. So it will go there, and so how does it bind it? So there is some interaction of binding, some sort of binding, but mind it, there is no formation of covalent bonding. So these bindings are very weak, relatively weak. It comprises of hydrophobic interaction, hydrogen bonding, things like that, and even van der Waals force of attraction. So these three constitute this binding. So the drug, say for example, is bound to the micelle, so it carries it to the target, and whenever it goes to the target, if the target has more tendency to bind with the drug, then this drug will be released from this micelle and it will go to the target. That is the simple thing. And that is called endogenous, where the drug is directly released from the carrier to the target. But there are some occasions where the binding of the drug with the carrier is stronger than the binding of the drug with the target. And then if it goes there, then also it will not be given to the or transferred to the target. So then we add something more, and that is called stimulant. So where exogenous deliveries will be that one where an external stimulant triggers the release. So say for example it's a micelle, okay, it goes there, but the binding of drug, efficiency of drug with the micelle is stronger than the binding of the drug with the, say for example, target means maybe DNA. Okay, so it will not go, it will not be transferred to the DNA. So if we add some cyclodextrin, then what will happen? Cyclodextrin will take up this surfactant. Okay, so this micelle limit will be broken. So if it gets broken, what will happen? The drug will be released in water, aqueous medium, and obviously it will not like that one, because drugs are mostly aromatic. So it will immediately bind to the DNA. So basically this cyclodextrin acts as a stimulant. That's it. Okay. I am not going in these details because we don't have much of time. So forget about all these, coming to the skin. So what happened? This was in this experiment, the lipids or liposomes, they were used as carrier. So you see, this is lipid membrane and this drug is bound to it. Okay? And then whenever it comes to DNA and that goes into the DNA, maybe intercalated binding or maybe group binding, whatever it is, and it becomes free. So this is the transfer of, or that means drug delivery. Okay, that's one. The other one, this is micelle. Okay, that was lipid, so this is micelle. I'm not going into the detail. Again, scheme wise, this is the micelle. So this is the drug bound to it, and when it comes to DNA, again the same. It goes, it intercalates within the DNA, and the micelle gets free. That's it. And this micelle will go out with the aqueous ejection channels like urine, etc. Okay, these two were the examples of endogenous. Now, what about exogenous? In exogenous, you see, before adding or before going to these DX researches, of course, we have to be confirmed, we have to get the confirmation that the added things do not harm our target. Here it is DNA. So this is the circular dichromosome spectrum of DNA, the black one. And this is DNA plus sodium tetradecyl sulfate, another surfactant or micelle. And you see, there is hardly any change. DNA plus beta cyclohexene, there is hardly any change. So these are set elements. So you see, the true point is this. PSF, this is the drug. This is a micelle. Binding constant is something like 10.6. And PSF binding with DNA, binding constant is only 10.4. 5.10.4. So basically, this is stronger binding. PSF binds in a stronger way to the micelle. So it will not be going to this DNA. That's the problem. But now, if we add cyclohexene, that will break this micellar structure. So that will release the drug to the aqueous medium. Obviously, it will immediately go to the DNA. That's the basic idea. There are so many ways to confirm this thing. So what is the schematic picture? So this was micelle, okay, and drug was bound to it. It comes to DNA, but it doesn't go there. This drug doesn't go there. Now you add beta cyclohexene, and immediately beta cyclohexene takes up these surfactant molecules. So they will be released through water channel because cyclohexene is water soluble, and the drug will immediately go into the DNA. That's it. Now, just extending the idea to clean the body from inside. New strategy for expulsion of adsorbed drugs from cell membranes. Okay, we like say for example, for my case, I'm a patient of hypertension. So every day I take some medicine. So what happens to the medicines? They do good to keep me up, but they are all getting absorbed day by day, day by day. This is cumulative effect. So they are absorbed on the surface of the cells, membranes of the cell. And definitely there will be a day when the concentration of them will be very high and that will lead to cancer. Obviously. Of course, I am a cancer survivor already. Anyway, so I'm not going into the detail. So basically, let's go to the scheme directly. Yes. So since we know that the membrane of the cells are constituted by the lipids, liposome. So basically, we started our work in this aspect with the lipids. And you see, this is a lipid. So we first bind it with the drug. So this is the situation. So basically, this is the mimicking position of cell membrane. Okay. So this is the cell membrane is there, and the drug, excess drugs there, or unused drugs or exhausted drugs, they are all affixed there. And then if we use suitable cyclodextrins which can bind it, so then we can do this thing. So these drugs are bound now by the or within the cyclodextrins, and this lipid membrane gets free. There are some papers, you can just go through them. Now, after you can see at least three with different lipid system we have confirmed it, with different drugs like cationic, anionic, non-ionic, etc. We have confirmed this thing all in vitro. Now, after being successful to all these studies, we intended to see if the strategy is applicable to real cell membrane, and we did a very crude experiment, taking help of the lab of Professor Kolkata and HIT, who is no more. Very sorry to say. So here, the model drug Nilred was put into Chinese hamster ovarian cell. Okay, that's a live cell. And we use the technique of confocal microscopy plus, of course, steady state emission and then PCS PCR. I'm not going in there. Just I rather request you to see this carefully. I don't know if you can distinguish the color. If you see carefully, this is the live cell, and you see only the boundary is found to be red. Red dots are there. That means Nile red is bound to the membrane. So this is basically our mimicking system, that this cell membrane is catching all the Nile. Nile red is a sample of or representative of drugs. Okay, this is the thing. Then on the petri dish itself, we threw some cyclodextrin. This is a very crude experiment I told already. So we could see lumps of cyclodextrins there, these two. But you see carefully, this is the cell now, and the cell membrane is not now containing any red dots. So those red dots are migrated or moved to the cyclodextrin. So this gives a clear picture that this internal cleaning of the body is possible. How? Okay, to give the gross idea, say for example, I am taking this medicine every day for years, and the doctor may suggest me after 6 months to take a course of cyclodextrin. By the by, we have already established that cyclodextrin is within a certain limit of concentration. It's safe to body. So, in fact, many of the drugs you take all the day or every now and then, their carrier is cyclodextrin itself. So, the doctor may prescribe that, okay, for 3 weeks you take some cyclodextrin and the internal body is clean, and you go on with your normal course of this drug. One clever question may be there, sir, the drug is still within your body. Maybe it is within the cyclodextrin, but it is still within your body. Yes, that's a good question. But the thing is, cyclodextrin is a very friendly molecular system. It is highly soluble, or rather, quite soluble in water. So what happens? The drug is within the cyclodextrin, no problem. But cyclodextrin is soluble in water. So that will be excluded or excreted from the body through normal water injection channels like sweat, like urine, etc., etc. So effectively, your body gets clean. Okay. So I'm not going into some other strategies. There are some more few. There are some more, but for the time concern, I want to stay here only. Okay. That was published in Analyst, RSC journal. So what are the inferences? This strategy is applicable to CHO. Okay, this one is done. So what is the take home message? Take home message is to look at the things from different angles with open mind. Okay, to do research, you must have some projection. That's a must. But never be very busy. Don't ignore all other observations, because most of the research is done by your eyes. by your eye. If you ignore something, you are missing a lot. And then you can do it, then it is possible to develop imperative strategies simply from the logical extension of very simple and familiar notion. So these are